I think it's time to start. Welcome, everybody, on our seminar of Quantum Information and Quantum Computing Working Group in Warsaw. Today, our guest is Vinicius Rossi from University of Gdańsk. And the title of his talk is a linear program for testing generalized contextuality and an application for parity-oblivious multiplexing. Vinicius, please start.
Thank you, Wojtek. Thank you, everyone, for showing up. Thanks, Jarek, for the invitation. Vinicius, I'm from the University of Gdańsk. I finished my PhD 3 months ago, and currently I'm a postdoc there. I'm going to talk to you about what I've been researching in just two years, more or less. This is a long title, but it summarizes everything I will talk about. So I will start talking about generalized contextuality. Then I'll go for the linear program, and then go for the parity-oblivious multiplexing application. And I like to start with a motivation or with a story. I'd like you to think for a moment that you can cook, and that you live now in a new flat, and you have a nice kitchen, and you like to make pierogi. So you prepare a batch of pierogi, you eat some, you leave the rest in the counter. Before you go to bed, you check, they are all there. And then in the morning, when you come back, they disappeared. Since you're a physicist, you'll do what physicists do, and you'll repeat the experiment to collect data. So you start preparing batches of pierogi, and you notice that the experiment always happens the same. So in the night, the pierogi are there. In the morning, they disappeared. And you also notice that it doesn't really matter what is the context in which you prepare the pierogi. So whether it's Rossi or is with cabbage or with salmon, the data of the experiment is always the same. It ignores this context. So in the evening, pierogi exists. In the morning, they don't. After you collected a good amount of data, you go to the physics department and you start sharing this with your coworkers and see what they think. And your first coworker is a more down to earth kind of person, more pragmatic, and he says, "Well, I think kitchens are just weirder than we thought. You should not really bother about like what is happening here. It's just a feature of kitchens, and we will have to learn how to capitalize on that and develop new technologies." You speak to another colleague and he says, "Okay, I think there is a simpler explanation for all of this. I think maybe there's just an animal living in your kitchen, and when you go to sleep, it just comes out and eats your pierogi." Finally, you go and you talk with your colleague that is currently working in the philosophy department, and he says, "Well, to be honest, if you're preparing different pierogis, it should be the case that there is a different animal for each recipe, each batch of pierogi that you prepare, because I don't know, for him it doesn't make sense that the rats would eat a salmon pierogi or the cat would eat the Rossi." So this okay. This also provides an explanation, but it's a little bit conspiratory, right? So the animals now, they organize themselves in turns, and they check what is the batch that you prepared. They are watching you cook, right? There's an animal conspiracy happening. It so turns out that quantum kitchens are not compatible with the simplest explanation. So if we are trying to find a classical model for some quantum experiments, we either need to go with a conspiratory explanation, or we just kind of give up on classicality whatsoever. I like this story because there are actually many examples in quantum theory in which contexts play no role in the statistics of the experiment, and this is the central idea behind contextuality. So if you think about ensembles that are preparing the maximally mixed state, you can just pick equal distributions of the 0 and the 1, and you can pick equal distributions of the plus and the minus. But we know that this is just a maximally mixed state, and it doesn't really matter from which ensemble the operator came. We also have digit transformations. So I just bring here the example of the maximal depolarization channel. And this is invariant under Hadamard transformations, right? So if you just plug in the Hadamard transformation after this map, it's just the same thing. And finally, I think this is the most well-known example of context not mattering is if you have tensor product measurements and you ignore one of the outcomes, then you should also ignore the measurement choice of this agent on this branch. So there are many examples in which contexts are just ignored. And generalized contextuality is this notion of nonclassicality. Therefore, that would expect that the quantum experiment should admit of a non-contextual, an ontological model. So a model in which physical properties exist independent of observation. They are just there. And the statistics is just coming from Bayesian probability theory and Boolean logic. But moreover, we would also expect that these contexts for preparations and measurements and transformations, if you have them, should be irrelevant in this ontological explanation as well. So because they are irrelevant on the actual experiment. So this is a non-contextual ontological model, and if you cannot have this, then this is what we call contextuality. Of course, ontological models they're very similar in nature to the hidden variable models that we usually talk about in Bell scenarios. There's just the caveat that hidden variable models usually are just supplementing the Hilbert space with additional variables, and ontological models are a bit more general than that. You can go for more general modeling. But basically, you expect that there is a measurable space that we call the ontic space, and each point in the space is just a configuration of the physical properties of your system, the ontic states. And then preparing a system is just sampling ontic states, and detecting an outcome is just getting a probability out of an ontic space, given that you prepared of an ontic state, given that you prepared this system in this distribution. And of course, the data of the experiment should sum over all the possible ontic states because you don't have access to them. So it's just assuming that you are ignorant of what is the actual state of your system. But moreover, because this is just an ontological model, this model will be non-contextual if when things are equivalent in the operational level. So if they cannot be distinguished, then they are described by the same probability distribution on the ontological model. So if two preparations are equivalent, you have them described by the same distribution over the ontic space, and the same for response functions. So we know that in quantum theory, we can always construct an ontological model because we have Bohmian mechanics and this sort of construction, but they are not always non-contextual. Bohmian mechanics, for instance, is a very contextual ontological model. Okay, so why do I care so much about generalized contextuality? Well, it's a very well-motivated notion of non-classicality. It's very closely related to Bellman locality and Cauchy-Specker contextuality. Of course, it's stemming from this reasoning. And it in cases subsumes a little bit these notions. Of course, I mentioned hypergraph contextuality. Other notions of contextuality might be in this list as well. It's also very closely connected to the notion of classicality in quantum Darwinism, of detection of anomalous weak values are attached to the existence of contextuality. Macrorealism is a notion that has been rephrased recently to match this, and negativity of the Wigner function is equivalent actually to contextuality, and simplex embedding of GPTs, which is something that I'll talk about this slide after this slide. But also practically, generalized contextuality powers up a lot of tasks. So we can think about state discrimination, we can think about parity-oblivious multiplexing, which of course I'll mention in a moment, but also anomalous heat flow. You have detection of anomalous weak values I mentioned. And philosophically, generalized contextuality is stemming from a very well-established principle, which is Leibniz principle of this identity of indiscernibles. Basically, just precluding that if you have things that cannot be distinguished by any experiment, then you should not describe them as different objects, because this adds a conspiratory nature to your theory. Okay, so I think I'll start talking about simplex embedding because this is the notion that I need to talk about the linear program. And for that, I need to talk about operational scenarios. An operational theory is basically a set of labels. So you have preparations, you have labels for the preparations that you can perform, can have labels for the measurements. Of course, you could have transformations as well. I'm just talking about prepare and measure scenarios here because these are the scenarios I'm interested on. And you have sets of outcomes for the labels and the probability rule. So far, this looks very much like your standard Bell scenario or even the contextuality scenarios that you see in this device-independent approach. But an operational theory also comes with an equivalence relation, which is I'm representing since the beginning of this talk as this wiggly symbol, such that I say that two procedures are equivalent if they produce the same statistics for whatever measurement I have access in my theory. And the two measurement outcomes are equivalent if they produce the same statistics for whatever preparation I have in my theory. So now I cannot talk about device independence anymore because I need to know what are all the possible measurements and all the possible preparations that I can have in my theory. But this is actually very natural. Usually, this is something that you know or you can assume within some certainty. And of course, and then the operational theory is this tuple, so it's just the sets of preparations and the outcomes and the probability rule with this equivalence. And from that, you can just construct what we call a generalized probabilistic theory by so basically you just quotient this sets of labels with respect to this equivalence class. And you just map these to sets in the linear vector space equipped with an inner product, and the probability rule becomes the inner product. So basically, you are just kind of constructing a minimal mathematical framework to accommodate that can recover these statistics. There is a lot of caveats between the last slide and this one. Of course, I'm just being hand wavy here, but we can discuss more later. And I think this is worth mentioning that GPT is said to be strictly classical if it is simplicial, which means that the sets of states and the sets of effects of measurement outcomes are simplices and dual hypercubes thereof. And the probability rule, of course, is just inner product in the Cartesian space. Because in the simplex is just a generalization of a triangle, basically. So it's a very polytopic notion of classicality. So let's just summarize what I just said. So operational theories are just the sets of labels. So here in this green sphere, I have the preparations. I have PA capital and PA lowercase and so on and so on. So I can pick one preparation, I pick one measurement outcome, and then I plug into this probability theory. This gives me a real number. But as I said, this is not only that, because we also have these equivalence relations. So for instance, I could have equivalence relations that the PAs are equivalent to each other and the PBs as well. But moreover, I could have equivalences of the form PA plus PB is equivalent to PM, or with of course, with probabilities, some convex combination thereof. And the same thing should be true for measurements. So they come with, for instance, this trivial equivalence that there is a unique unit. So all of the measurement outcomes for a particular measurement will sum up to this identity. What from here to go to a GPT, what we are doing is that we are just mapping these equivalences, each equivalence to a single point in a linear vector space. And then the distribution of these points will be given so that the inner product is reproducing the statistics of your measurement. Oh, sorry. Yeah, I'm here. So basically, this is what I just said in the previous slides. What I'm interested on is this notion of classical explainability in the GPT framework, because I just mentioned earlier that classical GPT is simply shown. And we say that GPT is classically explainable if it can be embedded into a simplex, if it can be simulated by a simplicial theory. So basically, I just say that this is simplex embeddable if I have two linear maps, iota and kappa, so that the action of this linear maps over my sets of states and effects is just simplex, living inside the simplex. Of course, this needs to satisfy some other constraints. This needs to preserve discard. This needs to preserve the probabilities, of course. Otherwise, why would this wouldn't be simulated? And the key aspect here is that the existence of a simplex embedding for a GPT is equivalent to the existence of a non-contextual ontological model for the operational theory from which the GPT was constructed. So whenever I have an operational theory, I can always construct a GPT. Whenever I have a GPT that is simplex embeddable, therefore I know that there is a non-contextual ontological model for this operational theory. And also a key information that I want to share here is that there is always a finite amount of partial depolarization acting over either the sets of states or the sets of effects, so that the simplex embedding becomes possible. This is very important because this is actually what the linear program is assessing, is how much depolarizing noise you need to add to one of these sets so that the simplex embedding becomes available. And it doesn't matter in which set you're acting the noise for purposes of GPT. This sounds very tricky and convoluted, maybe, but it's actually just child's play. So it's basically classically explainable things are this pointy objects, and it's obvious that they fit in the box of classically explainable things. And sometimes there will be something that doesn't look like it is classically explainable, but it fits inside a classically explainable thing. So you know this is classically explainable, but there are things that clearly don't fit inside a classically explainable thing. And what I'm just telling you is that there's always some amount of noise that you can act on this strange structure, so that eventually it will fit inside a classical theory and it becomes classically explainable. So simplex embedding is actually a property of positive cones of the GPT. So it's not actually a property of the GPT itself, it's a property of their cones. So actually, when you were checking if a GPT admits of a simplex embedding, you are actually checking if a large class of GPTs admits of a simplex embedding, because there are many GPTs that will be described by the same cones of states and effects, which in cones by definition are just these sets of all the vectors you can produce with positive real numbers and your vectors on your sets of states and effects. But the important thing is that I can describe the cones by facets inequalities. So this is very closely related to, it's actually the same concept as characterizing facets in the polytopic scenarios, at least numerically. So you're just trying to, instead of, you can characterize a polytope by the vertices or by the facets, right? So basically, this is what I'm trying to do here. I'm just trying to characterize the facets of these positive cones. So basically, these are these operators that If they act over a random vector and this vector is entry-wise positive, then you know that this vector is in the cone. There are many tools that can do this, and once you have this, you can pose the linear program. So basically, you define an accessible GPT fragment because the linear program is more general than assessing the non-classicality only of GPTs. It can also tell whether a fragment of a GPT, so just a subset of the states and a subset of effects, is simplex embeddable. And then by accessible GPT fragment, what I mean is just that they don't actually are spanning the same vector space, and they are just described in the vector spaces that they span. And therefore, I just defined these objects, these maps I, that are just doing the job of fixing the inner product here. But for all practical purposes of this talk, we can just understand this as identities. So I just give a set of states, a set of effects, and the Born rule, right? The identities here. And from this, I can numerically very easily find the polytopes, the facets that characterize these cones. I can also naturally construct the polarizing process. If it's quantum theory, we know what is the polarizing map. There is only one, but as long as you provide what the maximally mixed state looks like in your theory, you can construct your own depolarizing map. And then it just becomes a matter of minimizing this R, which is the amount of partial depolarizing noise here, such that there exists this matrix sigma here, which is just basically processing facets inequalities. I will not go in details of the proof here because I would need to use diagrams, and I try to avoid diagrams as much as I could. But basically, the proof is just relying on the fact that embedded states or embedded effects are covectors of this cone. So they live inside the cones of positive states and effects. So basically, that's the idea, the heart of the proof. But okay, this linear program exists. So with the linear program, you can also assess.
I think, Wojtek, you guys must be sharing Office, and because of that, there is some, yeah. I see. So the linear program works like not for vanilla quantum theory, but for some fragments that are discrete somehow.
Yeah. So you couldn't plug in the full block sphere because I don't think you can reproduce it in computer. I'm not sure. So.
I mean, you can probably start with some discretization, and
it needs to be discrete. Yeah, it needs to be discrete. Yeah, that's the.
Okay. Thanks. That was just some conceptual thing. And other, if not, like, do you get some? I know what was the technical term, like semi. Like, okay, don't you get SDP in that case, or something like this, or like what was like or linear program over like infinite domain, something like this?
I'm not really sure because then you'd have an issue with the cones as well, right? The cones will also be infinite sums.
Sure.
So yeah, I'm not sure. I'm not sure how this would look like in. I don't know I don't think we approached this problem.
I see. Thanks.
Okay, I think we can continue. So please, Vinicius, keep going.
Okay. Thank you. So I was talking about the linear program, right? I just copied the definition here from the paper. So basically, what this paper is trying to do is to leverage this equivalence between generalized contextuality and simplex embeddability to get new methods of assessing contextuality. Because there is this broader problem of testing whether a scenario is generalized contextual, generalized non-contextual is often challenging analytically. Sometimes you can do it. So for state discrimination, for instance, you can they explicitly construct the ontological model, but in many cases it's just a no-go. And the result now we have is that we have a linear program, and we provide implementation in Mathematica and in Python. The version in Python is my favorite. I encourage you to use it when over Mathematica whenever you can make this choice. And okay, so basically this is what's happening. The code is available in GitHub, in Mathematica, and in Python. The program is easy to set up, and I will put it as a quote-unquote because we need to characterize the cones. And to characterize the cones, we use a Python library that is not actually very easy to install if you don't know how to code, if you're not very familiar with it. But if you're having any trouble, come to me and eventually ChatGPT will try to help you. Well, the code is open source, and everybody's very welcome to try to improve it. It definitely needs improvement for people who actually are programmers, because we are all physicists. And it's quick to perform, especially in Python, is a breeze. And basically, this is what the program does. You input the sets of states, the set of effects. You don't need to input all of them, just the extremal points, of course, because you take the convex hull of whatever you input. You can also add what is your discard and what is the maximally mixed state, because not always what you are inserting is quantum theory. GPTs are more general than quantum theory. And in this case, you need to provide this additional information. The linear program will then just assess this geometry and solve the linear program and spit out how much noise for the non-contextual model. So this quantity R is a good measure of non-classicality, in the sense that if it's 0, then you know that what you're inputting is non-contextual, and if it's greater than 0, you know that this is contextual. And usually this is all you want to know. But in this application for parity-oblivious multiplexing, we want to know more. We want to know whether this number, the actual value of R that this code is spitting out, means anything. Because sometimes it doesn't. So we had a previous work with state discrimination, in which we are using this linear program, and we are actually changing the noise model. Instead of the polarizing, we are using the phasing. And we find one scenario there related to state discrimination that is maximally robust to the phasing. So you need to the only dephasing that will destroy the proof of contextuality is the maximal dephasing. But then when you actually look at the success rate for the state discrimination, it's very low. It's a borderline classical. So this opened the question of, well, is there a scenario in which this robustness actually is telling how much useful, how much resourceful the scenario is? And then we looked at parity-oblivious multiplexing, which is one of the most popular tasks in which speculative contextuality is a resource. So basically, in this scenario, if you're not familiar, Alice will just randomly select a bit string, finite bit string, and then encode it in a classical system, in a physical system, and not necessarily classical, by preparing it with a particular procedure. And then she sends it to Bob, and the Bob will just randomly pick one particular bit to guess. And of course, you are interested with in how often can he guess it right. The caveat here is that no information about the parity of this string can be shared. And this imposes some particular symmetry to the GPTs, that the GPT fragments that you are going to work with. And of course, the resourcefulness of this protocol is usually quantified by the success rate. So the greater the success rate, the more useful the scenario is. We know that contextuality is what powers up this task. We know that for a non-contextual ontological model, the optimal success rate you can get for, we say n-to-1 parity-oblivious multiplexing, means that you're encoding a bit string of n bits into a physical system. And then it's given by this expression, but the optimal quantum success rate is known to be with the square root on the denominator, so it's strictly larger. So basically, we just use this our linear program on this scenario, and we are just immediately directly comparing the robustness that the code produces with the success rate. Because we want to know if this number actually can mean something. And we find out that the robustness of the polarization actually is a good coherent quantifier with a success rate. So a coherent quantifier in the sense that they have the same maximum points and minimum points. And the when one goes up, the other goes up, and vice versa. And we also see that well, robustness to the phasing is not nicely related. Is actually not interesting at all. But when you minimize it over all possible dephasing axes, this displays some convenient relations. It's not as good as the polarization, but it also has this property that the maximums and minimums coincide. There is something strange that I'll show in a moment. But the contribution in the end is that with this linear program, we can just actually assess resourcefulness for this task and possibly for others. So basically, this is what I'm saying. When we compare robustness to the polarization with the success rate, this is very nicely, very well behaved. The red plot is actually because we also recovered this analytically. And the robustness to the phasing minimized over all possible axes has this strange behavior because, well, basically, when you pass beyond some point, the minimal axis just changes and you start having this overlap. But it's worth seeing that if you're just interested on some interval, for instance, of values, this is still very good. This is still good enough. And in this work, we also, and I think this is something interesting, we recover a well-known result because it is known that in a qubit, the maximum number of bits that you can optimally encode is 3. So you can only encode 2 or 3 bits optimally in a qubit. If you go for 4, you won't be able to do it optimally. This argument was recovered before first by a geometrical argument. So basically, you just come from the fact that the qubit set of states is spherical. And you argue that a 3D ball cannot be partitioned into 16 non-empty regions by 4 planes, because this is basically what you're interested in doing if you want to optimally encode these things. And there is another derivation by non-locality arguments, which is a bit more general, because this geometry argument is very elegant, but it only works for the qubit. So it doesn't work for other quantum systems. And the non-locality argument generalizes this a little bit, basically uses the fact that there is a correspondence between this parity-oblivious scenario and the Bell scenario. And the argument basically goes that if you could encode for bits on a qubit optimally, then you would violate serial sum bound or something like that. We provide a new derivation of this bound, relying only on contextuality and simplex embedding arguments. There is a caveat, and I'll mention in a moment as well. So basically, the notion is that we, as I mentioned before, we obtain this analytical relation between the success rates and the robustness to depolarization. And this is valid for any quantum system, any dimension. And then the optimal task would therefore just have the quantum optimal success rate and the non-contextual optimal success rate. We know that both of them only depend on the number of bits encoded. So you get this relation between the maximal robustness you'd have and the maximum number of bits that you would encode. So if you can get what is the maximal robustness to the polarization for a particular quantum system, you can immediately conclude what is the what is the maximum number of bits that you can encode optimally in this system. The caveat here is that we use numerical tools to get this bound for the qubit, because we just had the linear program, and we could easily just sample an increasingly large numbers of states and effects until we are almost covering the whole block sphere, and we reach this value that it's never half, it's always bordering half from below. So this must never be 4. That is the conclusion we get. But and of course that this can easily be done for different quantum systems, but this is a numerical estimation. So this is not an analytical derivation of the result. So as long as you are trying to get a numerical guess on how optimally you can encode this bits, this is going to work just fine. Okay, and I think I'll send the message here, the takeaway message. Generalized contextuality is a well-motivation notion of non-classicality. I will always try to motivate people because I think it's an engaging notion of non-classicality, and you can exploit this equivalence with simplex embedding to get numerical tools. And my job here and my stronger takeaway message is that if you are working with non-locality, or you're working with Cauchy spectral contextuality, and you are using these numerical tools, you are more on the numerical side of things. Generalized contextuality is coming with numerical tools as well. So if before working with generalized contextuality wasn't interesting for you because it was more foundational, analytical derivations and so on, now we are trying to come with tools for people to start working on this. And we show how you can just we just showcase how we can use this program to explore the parity-oblivious multiplexing task and possibly other scenarios, which I have a bunch of ideas to discuss. So thank you for your time. I think I'm within the time range, so I'm open for questions.
Thank you very much for interesting talk. And now it's time for questions or remarks.
I have a question.
Please.
Just following up on what I asked earlier. So is it known what is the, let's say, white noise robustness for, let's say, being non-contextual of, say, quantum theory in the dimensional system? Are such results known? Because probably eventually you'll be syntax embeddable if your objects are noisy.
Sorry, can you just repeat? Because
yeah, like just imagine you have a qubit, quantum theory on a qubit, and you would like to, I mean, okay, it's like not strictly related to your talk, but a bit related. But because I was not following on literature on this subject that much. So imagine I have a qubit quantum theory, and I want to know, I add this white noise as you are doing, and I guess eventually I will be simplex embeddable, or I will be spec and non-contextual. So for like, is it known what is the dependence on D of this, when I become simplex?
Yeah, no, I don't think this is known. I think this is something that we immediately had the idea of exploring when you developed the linear program. I think this was actually a project with a master's student, but I am not sure why it didn't happen. But yeah, but this is a question we made, is like, what happens when you increase the dimension, or what happens when you increase the number of extremal points on your set? So we are thinking about things. So we are currently working on a project with people ask a lot about typicality of non-contextuality, typicality of non-locality, and typicality of things, right? In which you just fix the number of parties and the number of measurements, and then you just generate samples of random samples of states and measurements, right? And then we are asking, can we just do the same question for non-contextuality? Is this interesting so far? So this is also something we are working currently.
So that's okay. That was one question. Can I have another one? So it would be like, so I understand that you have a linear program for this visibility. So oftentimes it makes sense to start the dual of a program, right? And in some cases it might have some operational meaning. Right? Did you explore something like this?
No, I had this question as well. So I need to do the disclaimer here that I didn't write the code. Who did write the linear program is Ali Wolf for Polymer. And I'm working with Belen and John, and they did all the thinking that led to the linear to the linear program. And I also work in the importation for Python and so on. So I understand very well how the linear program works. But I'm not a programmer myself, and I don't know how linear.
No, I don't mean I don't mean programming. I mean like you start.
Yes, I understand. So
yeah.
what I'm going to is that I made this question myself, and I asked my coworkers, but nobody knew how to reply. And I'm yet to meet Ali Wolf and discuss all the programming questions I have about this program, but I actually don't know what the dual has to teach us.
Sure, but because for many, for other areas, when people like for quantum measurements, like simulability of quantum
SDP
measurements,
always comes with the dual, yes.
Or like SDP or like some convex program comes with the dual, and it might have to do with some like discrimination game or something, or like optimal witness somehow.
Some inequalities for something like that probably.
Thanks. That's it from my end.
Are there any questions or comments?
I wanted to ask about this typicality. So do you plan to study it numerically, or you plan to use some methods like, I don't know, random matrix theory, Gaussian unitary ensemble, stuff like that?
I think it's so far we are working with it numerically. We are just sampling. We are using just libraries that because there is the problem when you're sampling states and effects, right? You need to get the higher measure right. So we are just sampling an increasing number of states and effects. Currently, all my projects involve this code somehow, and all of them are getting the same error because we are trying to go bigger with dimension, with the amount of number of states. So I'm just trying to push this code further in what it can process. But yeah, we are just going very numerically, very try hard. Just add a bunch of data here and see what happens.
Okay, thank you.
Anybody else?
Well, I would have one question. Can you hear me actually?
Yes.
So at some point you mentioned that you can use, use this program for Bell locality. But I guess that with that program we could check whether a point is non-local, right? Or belongs to the classical set.
Yeah, I think the connection I made with locality is that because there are these programs that characterize facets with double description, Motzkin, elimination, this sort of stuff. And I'm just mentioning because I just made this mention because a lot of the people who work with this are actually using the same tools that I am using numerically. But I wouldn't use this program to study non-locality because I know that the connection between non-locality and generalized contextuality is actually trickier. There is a work from David Schmidt connecting Bell scenarios to contextuality scenarios, and I think they have a numerical program there that converts the inequalities or something like that.
That does what? Can you repeat?
I think it converts inequalities from one to the other, I think if I remember properly, I think this is what it's doing.
Okay, and well, can I have another question?
Yeah, of course.
So there's this Lasserre hierarchy, right? I mean, it's like NPA with commuting observables. So it also allows you to bound the classical set from above, right?
Mhm.
So has anyone tried to implement this type of hierarchies for contextuality?
I think I know of two hierarchies for aspects of contextuality, but I think the issue with the hierarchies here is that they usually are device independent, right? They usually are not making any assumption about the dimension of the hybrid space.
Well, but
And
I
this
guess
is-
you can also do that, right?
Yeah, I think you can. Yes, so I think the ones that I know are doing this, but I don't know if they are from where they are coming. It's I think Anubhav Chaturvedi is the person that comes to my mind. I think he is working on this, or he worked on this in the last 2 years. Yeah.
But then, so what would be better? I mean, to use linear programming or the laser hierarchy? What is, in your opinion, faster or more efficient? Well, I guess that the laser hierarchy gives you a sequence of sets that approximate the classical set from above, from outside. So
yeah, I will check if I imagine that you would just check if your data is inside or outside one of the levels, right? Well, I don't know. I haven't used this. I think this linear program is more immediate with the question. It's actually try hard checking if this has an ontological model or not. This, however, has limitations, right? This is only prepare and measure scenarios. So if transformations matter for you, or if you have some non-trivial equivalence relations between transformations in your scenario, or if, I don't know, compositionality is something that is very important in some GPTs beyond quantum. So these are scenarios in which if they have some contextuality that is coming from these things, this program would miss. Because usually you can just say that everything is a prepare and measure scenario, but sometimes this details that you are just lumping into the transformation, the preparations or the measurements, they actually matter. So maybe a hierarchy would not miss these things. This is what I mentioned.
well, I would say that it might be that well, the first levels of the hierarchy are more efficient as compared to linear programming, right? But okay.
Yeah, I believe so.
Okay, thank you.
Thank you.
If there are no more questions or comments, then Vinicius, thank you very much for your talk.